Welcome to Review Lab 2, everyone. We're going to start with You Asked For It. I delivered another derivation. This is one of the spiffiest derivations out there. So I think you're really going to like it. If you don't like it, just talk to Mr. Odom. He feels very strongly about this derivation. He's a big fan. He might have created it. I don't even know. So make sure you check with him. Send him an email or something like that, maybe. Anyway, a bunch of equations. I don't know if there's some like dramatic foreshadowing with these ones over here or something like that. But let's read the situation, draw a picture, and see if we can figure this thing out. A Hot Wheels car, mass M, is released from rest on a hill of height little h. Careful with that. That rests on a table of height big H. The ramp is set up so that the car leaves the table with a horizontal launch velocity. Jam full of important information. Derive an equation for the range of the car, delta x, measured from the edge of the table in terms of constants and the variables listed above. I like pictures. They say a picture is worth 1.0 times 10 to the third words. So maybe we have a little ramp type thing here. Here's a little car on top, racing stripe. And here's the edge of the table. Notice we set this up so when the car leaves the table, the velocity is going to be perfectly horizontal. And then let's keep track of our h's. We called the height of the hill, little h, and then the height of the table on the floor, big H. Make sure we keep those straight. So the second half of this problem, when the car becomes a projectile and leaves horizontally, that's going to be pretty familiar. We actually just derived a version of that equation on a piece of paper that I still have. Look at that. We just derived it. So if you want, maybe we can just copy that one there. So this derivation for the range says there's velocity times root 2h over g. So that's going to be for the projectile here. So the range is the velocity, which we still don't know, but that's going to be our launch velocity here, times the square root of 2. I'm going to put in big H here because we're talking about the projectile from this height here, divided by g. So why can't we just leave it there? Well, the problem says in terms of constants, so we got some constants in the variables listed above. The only variables listed above are m, little h, and big H, which means we can't leave this v lying around in the equation right here. So we're going to have to get rid of that and then use some other constants, hopefully, in its place. But we'll set this range equation aside. If you don't know where this came from, check the last video. We derived it. This is the range for a horizontal projectile launched from a height of h. Cool. Boom. Done. Love it. That's why we did it. Now we need to figure out what the speed is or what the velocity is at the bottom of the hill. The car starts from rest, and then it's going to end with kinetic energy. I've been told a bunch about these amazing things called LOL charts. If you are a master of the LOL charts, that seems like a great thing to use here. But you're starting with all gravitational potential energy at the top. Then at the bottom of the hill, we have all kinetic energy. If you just focus on this part. Technically, there's still some potential energy because we're still on top of a table. But you can choose to focus just on this part because we only care about speed at the bottom of the hill. And we're just going to isolate in on that. So we're starting with gravitational potential energy. I guess the AP equation sheet likes the symbol U for that, sub G for gravitational. And that is going to get converted into kinetic energy, assuming we don't lose any to friction or heat or anything else like that. So this is just going to be mg delta y for our gravitational potential above our 0 point, which we're going to define here. So the car has mass m, g is g, and we are at a height of little h above our 0 point. That's going to equal the kinetic energy at the bottom because all of the potential gets converted into kinetic. 1/2 mv squared. Cool. So we're going to combine this equation with this equation. Hopefully we can solve this one for v, substitute in here, and I think we'll be left only with the constants that they're looking for in the problem. So let's solve this for v. First thing I noticed, we have an m on both sides, so you can divide by m to get rid of those. Let's multiply by 2 over here. So we have 2 times g times h equals v squared, which means the velocity at the bottom of the hill is going to be equal to square root of 2gh. Substitute this into our equation up above. This is where the fun happens. I'm pretty excited. So v is root 2gh, bing, times root 2 big H over g. That g is part of the square root, by the way. Sorry if that was confusing. And let's multiply these together. If they're two square roots, we can just do one giant square root and have 2 times 2 is 4 times g times little h times big H all over g. Oh my goodness, it's happening. It's happening. Oh my gosh. So we can pull a 4 out if we like, because the square root of 4 is 2. So then we have 2 times the square root of h times big H. Could it really be that simple? Amazing. I love this derivation because all of that stuff comes down to just 2 measurements, the height of the hill and the height of the table. Those 2 things determine the range. Notice there's no mass in here. This, oh, you can't see that. This was just a red herring. The mass of the car doesn't matter. The gravity doesn't matter. It doesn't matter what planet or moon or whatever you're doing this experiment on. The only thing that affects the range is going to be the height of the hill and the height of the table. That is amazing, and we're going to put that to the test. That is what we're going to do for Lab 2. I'm super excited. I hope you are too.